Going back.
Yeah, we'll do a little bit of brainstorming at one point so that you can kind of see with your small groups, is there anything that you remember from Algebra 2? Okay, pull it back. I know, it's asking a lot coming back from winter break and everything.
Referring to like degrees.
Okay, first thing we're going to talk about are the angles in standard position, so that we're all like understanding angles and thinking of angles in the same way. So we're kind of thinking about angles like on an XY coordinate plane here in Honors Pre-Calculus. And you should have you should have seen like angles in standard position back in Algebra 2. We have in standard position, we have the initial side and the terminal side. And in order to be in standard position, it's really important that the initial side is on the positive x-axis. So if you were to go x equals 1, x equals 2, x equals 3, you're moving to the right. That's where your initial side always is. So you're always opening from the positive x-axis. Your terminal side, or your angle, then always opens, a positive angle opens counterclockwise. So you can see like the red is saying what direction my angle is opening. And then it ends somewhere, we call that the terminal side. Now, being familiar with that as the terminal side, that could be really helpful in some of the definitions that we'll be seeing later in the chapter. So I'll say like where the terminal side lies, and then you'll know, okay, that's just wherever the angle opens to. So maybe you want to jot something else down here, like positive angles are counterclockwise, and negative angles go clockwise. Any kind of reminder that you'd like to set for yourself in your notes, you're welcome to write that down. Seem familiar?
Okay.
Okay.
I learned.
Oh, you did it in physics this year?
Yeah.
Okay, good. Cool. Okay, so then we're also going to talk about radians. Okay, now it's probable that you saw this animation last year, and what I'll have you do is if you want to jot down the definition of a radian, go ahead and do that now, and then I'll talk about like what that definition means in that animation that you're seeing. So 1 radian is the measure of an angle. So it's just another way to measure an angle besides degrees. It's the measure of a specific angle that intercepts an arc of length r, where r represents some radius of some circle. Okay. So we see that in the image down here, and I'm going to let it run through its regular thing. And we'll restart it at the beginning when it's in standard position. Okay, so it's going to start by getting some radius, and it could be any size circle. It could be a smaller radius or a large radius. If you pull that radius outside of the circle and curve it to fit the circle, and then with those two endpoints of that radius, you draw an angle, that represents 1 radian. That's how much a radian is, just like how a degree is 1/360th of a circle, right? Okay. So that's what we're doing. And then you can see, like, in that top quadrant 1 and quadrant 2, you can get pi radians, a little bit more than 3 radians. It's actually 3.14. So pi radians is in 180 degrees, and 2 pi radians is in 360 degrees. Does that seem familiar? Okay, so maybe you want to jot down something, pi radian equal 180 degrees, 2 pi radians equals 360 degrees. And then you might know some other angles in radians and what they relate to in degrees, most likely. That's great. Estimate how much is 1 radian in degrees. I talked about this last year. About how many degrees would you say was in one of those? Maybe 45? 50 something. It's a little bit more, it is more than 55. It's really close to 60. It's like 57 point something. Okay, so that's why, like, you know, like, think about it. We can get 3 and a little bit more into 180. So 180 divided by 3 would be about 60. So it's just a little bit less than 60. Okay. Mathematicians and probably physics scientists like radians, because radians is based off of the characteristics of a circle. It's like innate characteristic of its radius, and not some man-made degree. Like, we just created that and said this is how much a degree is, and this is how many degrees go into the circle. Whereas radians, it doesn't matter what it is, that's always going to be true about how many radii go into the circle or go around the circle. Okay? So that's why we like to, especially in higher level math, we like to measure angles in radians. Okay, so I'm going to give you a little piece that you can put into your notebook. We are going to go over these again next week when we get started on our unit circle. But these would just be nice for you to have handy things. As you look around that circle, are you recognizing some of those angles, like 45 degrees is pi over 4, and 60 degrees is pi over 3. You've probably seen all of those before in Algebra 2. I got some tape spelled it out for you. Good. Tape that in your notebook, you may. So you've been exposed to these angles. These are like the angles, you know, where you keep adding 30 or you keep adding 60 or you keep adding 45 around the circle. And they're going to be really important to us as we progress through our trig chapters, chapter 4, chapter 5, chapter 6. So, you know, you've been exposed to them once before. Maybe it'll be a little bit tough here at the beginning to remember that 11/6 pi is 330, but eventually that should just kind of be like common knowledge to you. So you'll be able to go in and out of radians and degrees for these special angles. Now, we should be able to then draw sketches of angles based on what we know, and like this would be kind of like an estimation. You may or may not have that specific angle on the picture that I've drawn for you, but you'd be able to determine in what quadrant and to which axis it would be closer to. So if you were sketching 225 degree angle, okay, things I would look for on your sketch, so you're thinking about your very first problem set, what would I want to see? I'd want to see that you have an initial side on the positive x-axis. You're opening counterclockwise 225 degrees. In what quadrant will you land? Quadrant 3. That's actually on our circle that we're just looking at, right? It's one of our special angles, so we're going to draw it in quadrant 3. And I would also expect you to show that direction that you went. And so I'd be looking for that arc to show that it's 225 degrees. We could also sketch something like negative 120 degrees. What changes about negative 120? Goes the opposite direction. We should draw our initial side in the positive x-axis. Now instead of going counterclockwise through quadrant 1 and quadrant 2, we're going to be going clockwise through quadrant 3 and quadrant 4. And here you won't be able to necessarily use the numbers, like it's not going to be the 120 in quadrant 2. We're actually going to end, so if we're thinking about this is our 0 degree, this is our negative 90, and this is our negative 180. So we're somewhere in between those in quadrant 3. And then again, you should sketch that arc so we can see you're going 120 degrees clockwise. Now, the last two that I have are the ones in radians. And the best thing I could say about radians is I really focus, as long as it's in terms of pi, I really focus on the fraction pieces. Like within the fraction, where does it belong in terms of the other fractions like 1/6, 1/4, 1/3, 1/2, 2/3, 3/4, so on and so on. So if I were looking to graph 3 pi over 7, I would focus on 3/7. In terms of my fractions for pi, this is 0 pi over here on the positive x. This right here is 1/2 pi. And then when I get to 180, I'm back at 1 pi. So is 3/7 in between 0 and 1/2? Or 1/2 and 1? Is it going to be in the first quadrant or the second quadrant? The first quadrant. 3/7 is not a full half, right? What would be half of 7? 3.5. So this 1/2 pi up here, that would be 3.5 over 7 times pi. So we know that if we're just doing 3/7 pi, we must be just a little bit less than that. So I know that I should land somewhere in the first quadrant. And I should actually probably be very close to the pi over 2. So even though 3 pi over 7 does not appear on that circle, I still can place it in the correct quadrant using my fraction. What about 7 pi over 3? A full rotation and then a third. Okay? Remember, a full rotation is 0 pi or 2 pi, right? So if you think about 7/3, 7 divided by 3 is 2 and 1/3. So that means I'm going 2 pi, so a full rotation, and then just a third more. So again, this one is going to end up in the first quadrant. I'm going to go around 1 time and then a third. And remember, when you draw these, if they have multiple rotations, draw the spiral. If you could go around 2 times, then draw a spiral 2 and then some more. Did you have a question, Tegan? All right, so that's, just one of those things you need to sit with and concentrate on, especially when they're given to you in radians. Now, be very careful. If it doesn't have pi in it, and it just said like 3, and it didn't have pi and it didn't have degrees, then it would mean 3 radians, and you would have to figure out, like, where is that? 3 in radians would be between 3/2 pi and, not 3/2 pi, would be between pi over 2 and pi, because this has got to be like 1.57 and this is 3.14. So if we just said 3, we'd be really close to pi radians, 3.14 radians. So be careful if they're giving you decimal radians. If I want you to graph in degrees, we'll put a degree sign behind it. There is not a degree sign behind the number. we assume now that it is radians, not someone forgetting a degree. Okay? All right, now we're going to do a quick brainstorm. Okay, what other types of things do you remember doing with angles, whether it be in degrees or in radians from Algebra 2? So with your small table groups, and you guys can decide if you want to do partners or if you want to quick meet in the middle and kind of join forces there. So what kinds of things do you remember doing with these radians and degrees, if anything at all? Go for it.
Oh yeah, like didn't memorize the circles too, and like they have like little quizzes. No. Yeah, no. Where did you memorize the circles? Or no, like that, stuff like that. Oh, 45. Yeah. 60, 90. No. I'm getting like flashbacks.
A great feeling. No. Now, like Tatum, anything you remember doing with angles?
I just remember like switching in between degrees and radians, and then like remembering cosine and sine and angle and what it was.
Okay. Cool. Abby, Sarah, McKenna, you guys got anything else to add?
We were converting when you remember like the 180.
Multiply by 180?
Like it was like
Okay. Siobhan, Tatiana,
Like-
Caitlin.
The 45, 45, 90-degree triangles, and 36, 90-degree triangles.
Anything else? Okay, Tegan, Hallie, anything else to add there? Okay, so we are going to focus on converting today. So we'll have some converting. There are some other things. I'm going to pass out cards to your groups and have your groups kind of see, okay, once Ms. Conkey gives us this word, do we remember this thing and how do we do it? We are eventually going to get to this whole, like, you know, what is the cosine of 45 degrees? Or what is the cosine of pi over 6? Do we know it? Yeah, we should know it right away. Raise your hand if you used the unit circle last year. Okay, so most people had some kind of experience with unit circle. If you didn't see the unit circle at all, no big deal, we're going to introduce it. And in order to do all that stuff, what is the cosine sign of any given number around that circle that I just had you tape into your notebook? We're going to be using the 45, 45, 90 and the 30, 60, 90 triangle. Yay! So we're going to do that tomorrow. Okay, we're going to focus on 30, 60, 90 and 45, 45, 90 tomorrow. Cool. Okay, so I will give you and your group something to talk about. See what you can come up with. How do you do it? What do you need? You're not acting. I like how we added subtraction it.
Nice.
I remember it.
I recognize it in my memory.
I got it. I'll still write it down.
Something ringing a bell right there? Okay. Easy one.
Oh.
I like those.
As long as like we're doing like converting, like I can do that like left. But it just scars me so much.
You guys feel comfortable with complementary?
No, probably not, because that's, yeah.
Okay, let's come together. And I think Tatum and Noah, you guys had the conversion card. So we already kind of talked a little bit about conversion. If you guys make a decision between like the pi over 180 and the 180 over pi, which is which? Okay.
So degrees to radian is pi over 1.
Good. Now, how do you decide that? Do you have a method for remembering or deciding?
Well, when it's radians, the pi is on the top. So when you have to multiply it by fraction, remember that the pi has to be on the top of the fraction.
Very good. It's all about like, like a conversion or a cross canceling. I think in chemistry maybe they call it stoichiometry. Does that sound familiar? Where like you go from miles to inches or whatever, one by one. So what we're doing here is we're taking something that is in degrees, we'll multiply it by a conversion factor. We need the degrees to cancel, so numerator degree will cancel with denominator degree, and whatever's in the numerator right there, that pi radian, that's going to give us our final answer in radians. Okay, excellent. And then vice versa, we would multiply by 180 over pi. So just to make sure we're all on board with this, 225 degrees, if we want to change it into radians, we would multiply by pi over 180. If you're able to use a calculator, you could do 225 divided by 180. Don't put the pi into the calculator, leave it in terms of pi, and then change that into a fraction. If it's in the no calculator part of a quiz or a test, which you know there are no calculator sections, then I would just work on reducing. Like what goes into 225 and 180? 5, definitely. So let's at least reduce it by 5. This one would be, what, 445 divided by 5, and then 18 or 180 divided by 5 is 36.
Whoa.
And then do 45 and 36. Could you reduce them any further? Yeah, they're both divisible by 9. So if they're both divisible by 9, my final answer is going to be 5 pi over 4. Now, that's one of those that's on that circle. It's one of them that is like the 45, 90 special right triangle. So by the end of the chapter, you're not going to need to actually do the conversion on that. You're going to know 225 is 5 pi over 4. But when in doubt, you can always multiply by pi over 180. And then vice versa, I got 2 pi over 5. I want to change it into degrees. Now multiply by 180 over 5. The nice thing about this one is if your radian was in terms of pi, what happens to the pi? They'll cancel out. And then sort of like the same process there, if you want to multiply across or do some cross canceling, I would probably do this piece right here, 180 divided by 5. So 5 goes into 5 one time. We already know 5 goes into 180 36 times. And then I just have 2 times 36, which is 7. Again, if you have access to a calculator, you can check those things in the calculator, no problem. Any questions or concerns about conversions? Okay, my next group, I think is my middle front group here. You'll have some information about complementary and supplementary angles. What did you guys decide about complementary and supplementary angles?
Favorite complementary angles is something out of 290.
And these are specifically angle pairs. So we're talking about 2 angles can be complementary, 2 angles can be supplementary. We wouldn't really have 3 angles that are complementary, and they're just a pair. Did you guys talk at all about radians?
It would just be the add to pi over 2.
Very good. So I would add that complementary angles will add to pi over 2 or add to pi. Probably most of us, if we need to brush up on anything, we really need to, in complementary and supplementary, need to brush up on the radian portion of it all. Okay, so just kind of be aware of that. If you want to find a complement, you would take pi over 2 minus the angle. So can I use theta for my angle? And you certainly could do 90 minus theta. That would be very easy. I'm not going to review that with you, but pi over 2 minus theta. If you want to find a supplement, then do pi minus theta. And that's in radians. So just to practice our radians, because I think that's the place where probably most people are going to need the most guidance there, can we find the complement and the supplement of 2 pi over 5? I mean, essentially, we're going to take the thing that they should add up to and then subtract the piece that we know. So the easiest one there to me is pi minus 2 pi over 5, the supplement. You take 1 pi minus 2/5 pi. How many pi's are left? 3/5 pi? Because 2/5 pi and 3/5 pi would add to make 1 pi. And so that should be a pretty easy one. What are you going to need to do on the complement? You're going to need a common denominator, right? So good common denominator for 2 and 5 would be 10. That would be 5 pi over 10 minus 4 pi over 10. And so we'll get pi over 10. Now, what would happen if you did pi over 2 and you subtracted the angle and then the answer was negative? What does that mean? It was already more than 90, and then does it have a complement? No. So don't give me a negative angle as a complement. When we talk about complementary angles and supplementary angles, we're talking about a pair of angles. We're talking about a pair of positive angles. So you could say if it came out to be negative, or if you recognize that it said find the complement of 100 degrees, no complement. That's your answer. You don't give an angle for that. Very good. Any questions about complementary, supplementary? Okay, my group right here, what did you have to enlighten us about?
Coterminal angles and radians.
Oh, coterminal angles. That's one of those things where I think when I hand out those cards and you see the words, you're like, oh yeah, I remember that too. Okay. So coterminal angles. And can you tell us what was the deal with coterminal angles? Did you guys talk about that?
They're essentially the same angle, but they might just go out the whole circle.
So I'm going to say same angle, different measures. Meaning, if you didn't have that little red arc telling you what direction you went, counterclockwise versus clockwise, or I went around one whole time and then some more, you wouldn't be able to tell the difference if that piece wasn't there. They look like exactly the same angle. The terminal side is in the exact same spot in whatever quadrant. Okay? So it really is the same angle, just a different measure. And we use coterminal angles a lot to get our angles to be those angles on that little yellow piece of paper you put into your notebook. If I can make the angle 225, then I already know all the stuff I need about 225. And I don't have to redo all that work. Okay, so that's the idea there. So you kind of said same angle, but maybe an extra rotation. So did you talk about, like, mathematically, how did you find coterminal angles?
You either add or subtract 360 for degrees or add or subtract 2 pi.
Very good. Add, subtract 360 degrees or 2 pi, depending on if you're in radians or degrees. Now, some people in Algebra 2 felt really uncomfortable in radians, so they always did this thing where if it was in radians, they would change it into degrees, they would do the thing with degrees, and then change it back into radians. We want to move away from that, right? I get that. That's like a comfort spot for us. But like you're moving up and you want to like say, okay, this year I can tackle those radians. I can do it in radians. I can add 2 pi. Now, whether you add or subtract 2 pi as we go through the chapter, that's going to depend on, like, if you have a negative angle, you're going to be adding the rotation so that you can get something positive that would show up between 0 and 360. If you have something that's greater than 360, you're going to be subtracting rotations until you get into that realm of 0 to 360 that we want. So let's find coterminal angles for 2 pi over 5, one positive, one negative. Because it's in radians, I'm going to just add a full rotation in radians, get right back to where I was. So I'm going to add 2 pi. And this, by adding a full rotation, I'm going to get a positive coterminal angle, okay? Now, what do I need in order to be able to add there? Same denominator, because this is really like 2 pi over 1. So it'll be 2 pi over 5 plus, this will be 10 pi over 5, which gets me 12 pi over 5. And then for my negative coterminal angle, I'm going to always go back to the original angle, not to my 12 pi over 5, because if I just subtract the rotation, then I'll be just going backwards that step. So go back to my original 2 pi over 5 and subtract 2 pi, which we now know is 10 pi over 5. That's enough to get me into the negative. If that angle had been like greater than a full rotation, maybe I would have needed to subtract 2 pi twice to get a negative coterminal angle. You're looking at this and you're thinking, man, I had a hard time with this last year in Algebra 2, but now it seems so easy, doesn't it? It's funny how that happens the second go around. Okay, so you're like, oh yeah, I think I could do this. I could do better this year. That's a good feeling. Any questions, concerns about coterminal angles before I leave it? Again, the idea there is that it really is the same angle. All right, Hallie and Tegan, you guys had my last bit, arc length and area of a sector. And the first thing you guys said was, what? Before I came and talked to you, you were like, what was going through your head? Well, you knew what? There's some kind of formula, right? And Hallie even said, there was a formula, I wrote it on my notes. She had a note card for a file. That's how she knew, right? Okay. So this is now our second go around. So we'll see the formulas again, and then maybe this time they'll kind of stick with us a little bit longer. So did you guys? I encourage them if they couldn't remember, look it up in their book or on Google or something. Did you remember the formula?
You got close.
Oh, okay. What is the formula for arc length?
Oh, I have arc S equals R.
Very good. S equals R times theta. That's very simple. Radius times theta, the angle. Okay, now, there is a little piece here. Theta must be in radians. Okay,
Yeah, I already know this.
you what?
The whole unit about this, right?
In physics?
Yeah.
Nice, yay! Okay, and then area of a sector?
1/2, well, 80 equals 1/2, or square root of theta.
There you go. And again, the same rule applies here. I put on their card specifically, give me the formulas in radians. So if there was one sort of like pothole that I could warn you about, it's just putting in a degree right there, right? So I mean, like, practice, 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 and while you're practicing, be really cognizant about the formula, like this requires radians only. So what we're doing is we're looking at it like, the nice thing about radians is it's just like a fraction of a circle, right? We know that there's 2 pi in the full circle, and so when we get an angle in radians, we're just getting whatever fraction of the circle it actually is. Versus if you look up the formulas for arc length and area of a sector in degrees, they have to add that fractional piece back in. So you're going to see always they're going to have like their theta divided by 360. So that if you had a 90-degree angle, 90 divided by 360, you have 1/4 of the full rotation. If we just have pi over 2, we don't need to do that because now we have that fractional rotation piece. Okay, so that's kind of like where that comes from. Now you'll have some questions on your homework where you have to work with arc length and area of a sector. So find the arc length with radius of 5 inches and angle measure of 120 degrees. And I'll draw here what are we talking about? A circle, a radius of 5 inches, and then we've got 120 degrees. The arc length is just a fraction of the circumference. So not the whole circumference, just a fraction of the circumference. I hope you're not getting 600. Anybody getting 600? Good. If you're getting 600, that means you're leaving it in degrees, but you've got to change this theta into radians. So you can do a conversion right there, 120 times pi over 180. Anybody get that angle? 2 pi over 3, excellent. So then I can do the arc length very simply. It's just the radius times 2 pi over 3. And I'm perfectly fine with 10 pi over 3 as long as that fraction is reduced in use. Now if you want to know the exact length, like you're talking about distance on the earth or something like that, you probably want to put it into decimal to make sense. One final example to look at. If the sector formed by the central angle of 30 degrees has an area of pi over 3 centimeters squared, find the radius of the circle. So again, I'll draw a picture of what I'm talking about. Some radius. The area of a sector, I always think, like when I taught this in Algebra 2, I said it's like the pizza slice. Okay? It's the area of one of those slices. Again, another problem here that is giving you an angle in degrees. 30 degrees is really how many radians? Pi over 6, right? The smaller of that. 60 is pi over 3. Okay, so that's my pi over 6, and then really I can just plug those things into the formula for area. So I know that the area is pi over 3. That's equal to 1/2 times r squared times pi over 6. On the side there, multiply, it'll be pi over 12. Okay, and then you should come up with a radius of 2, I think. So pi over 3 equals pi over 12 r squared multiplied by 12 over pi. And you'll get 4 equals r squared, so r equals 2. Now you wouldn't do the negative 2 because the negative radius doesn't make sense. Your homework is on your gold sheet. We'll go over it tomorrow.